Yeah. All right. Hello, everyone. Welcome and thanks for making it to the last day of presentations. I'm sure it's all for me. So I'd like to make sort of a cheeky observation before we begin. So it's been really nice hearing a lot of perspectives about magnetic field from all, from all different points of view. But one pattern that I've noticed is that observers will typically talk about things like star-planet interactions or activity or spectropolarimetry, or generally techniques which are sensitive to surface magnetic fields or magnetic fields exterior to a star, for reasons which I think are not particularly surprising. But as a theorist, you really want to say things about internal magnetic fields. And so just to get to the point, I'm going to try and sell in these next 15 minutes the idea that asteroseismology is the most direct way to measure internal magnetic fields, which are in general could be many orders of magnitude larger than surface magnetic fields. Right? So the point is that we think that even when the magnetic field is not substantial necessarily at the surface, as long as you have a star which has a strong magnetic field in a radiative region, and it pulsates for some reason in G modes, then this might be able to do something for you. Okay. So let me just try and state the problem a little bit more generally, just to give some background. What is this? Okay, so sorry, thanks. Anyway, I can start over here. So what are G modes? G stands for gravity. I think it's kind of an interesting name, but really you should think of it as being fluid waves which are restored by buoyancy rather than pressure, which is what we're used to. Sort of P modes are just sort of these normal sound waves that follow a dispersion relation where omega is proportional to K. But the dispersion relation for gravity modes actually looks like this. So you have some frequency, and it's basically equal to the ratio of the horizontal component of the wave number over the total wave number, and then multiplied by this frequency scale called the buoyancy frequency, or the Brunt-Väisälä frequency. So here's just a profile of what this looks like, for example, in like a typical like 1.5-ish solar mass red giant star. And typically in, I would say most cases that I'm aware of, the G mode pulsations that occur in a star tend to have pretty high radial order, which means that they have a large quick oscillation in the radial direction. They have many nodes in the radial direction, or a small wavelength in the radial direction. Those are many ways to say this. And so basically K is approximately KR. And so you notice that unlike with P modes, the K appears in the denominator, not the numerator. And so in normal sound waves, we're sort of used to frequencies being equally spaced in frequency space. Mode frequencies are spaced equally in frequency space, but G modes are actually if you don't have any other effects besides buoyancy, they should be equally spaced in period. So this is called the period spacing. It's a very important observable in asteroseismology for the G modes. It's basically related to the integral of the buoyancy frequency over the relevant G mode cavity. And I've stated the problem so generically because it's pretty widely applicable. So all of these are examples of objects which might pulsate in G modes. And all of these, I think, except for the subgiants, pulsate in high order G modes, as far as I'm aware. So this is the picture when you don't have any fields. And let me just say that just by measuring this period spacing by itself, in the absence of fields and stuff, you can already learn a lot of things about the interior of the star, because in the case, for example, of red giants, this really probes the radiative cavity in the core of the star, which is something you don't directly see. And so just by measuring this, it's actually quite easy to distinguish between red giants, which are core helium burning or on the clump, and hydrogen shell burning or on the first descent red giant branch. And then furthermore, if you get the period spacing as a function of period, so not just one number, but as a function of period, you can actually measure sort of other stuff as well, like rotation or near core mixing. But of course, I want to talk about magnetism today. So what does that do? And the heuristic picture you should have in your head is that if you have some substantial magnetic field, it can shift the frequencies. And then if you have a stronger magnetic field, we think that you just suppress the oscillations outright. And so let me just, the first one of these is sort of like, has a little bit more historical precedent, by which I mean like just the last decade or so. So I'm going to talk about it first. So if I write down the dispersion relation for magnetogravity waves, so this is the G mode dispersion relation, but then I have an extra term, which is like the Alfvén frequency, and I assume high radial order G modes. If you set all of these terms equal to each other, then it turns out that there is a scale at which all of the terms are like basically buoyancy is comparably important to magnetism. And that defines this scale at which we think that you will start to get suppression. So you'll start to be resonating with Alfvén waves. So you can either state it in terms of a frequency criterion like this. In other words, sufficiently low frequencies will be suppressed by some magnetic field, or alternatively, you can just invert that relation and say, for a given frequency, I will suppress the mode if magnetic field is above some scale. And so this is the scale at which we think suppression happens, but more generically, it's the scale at which we think that there should be non-perturbative effects. So here's just an example of what I'm talking about when I mean that there's suppression. So here on the top is basically what 80% of red giants look like seismically in their oscillation spectra. You see there are these red peaks, which are the dipole modes, and they're pretty healthy in these top ones, but they're pretty suppressed in these bottom ones, which make up actually about 20% of the population. And then in contrast to that, the radial modes, which are the black ones, look identical. And the radial modes can't be G modes. So the idea is that, well, if it's not affecting the radial modes, it must be something in the core, right? And you can make a basic flux conserving argument to say that we're actually at the, red giants can achieve in their cores magnetic fields which are at the non-perturbative regime. So this is commonly invoked to explain somehow the suppression. And then more exciting recently, in the last year, there's been a claim of this similar phenomenon in a magnetic B-type star. So this is 6 solar masses, where basically they observed that the low frequency modes are missing. And that sort of corresponds to roughly a scale of like 500 kilogauss. So that's also, by the way, the scale that I'm talking about in the red giants as well. It's about hundreds to a kilogauss to a megagauss. But maybe, so in more recent years, in fact, in the last year, people have first been able to measure frequency shifts, not suppression, due to strong fields, which are not strong enough to suppress the oscillations over the whole frequency range that you measure. And so here's just what that looks like. So let me just break this plot down a little bit. The labels are a bit small, but basically, if you remember, I said that like for high radial order G modes, they are equally spaced in period. And so a corollary of that is if I go and I plot the period of a mode modulo like some period spacing, then I should get a vertical line. And if I do this and then there's some kind of curvature or something, then it's reflecting a departure from that asymptotic expectation. And then so what's being plotted here is actually this, but for the dipole modes of a red giant star. And you can see that if you don't have anything that symmetry breaks the spherical symmetry, then these should all be degenerate with each other. But in fact, if you have anything that breaks the symmetry, then it will actually break this degeneracy between the oscillation frequencies. And in particular, it's pretty straightforward. I mean, difficult, I would say. Maybe I shouldn't say the word straightforward. It's conceptually simple to disentangle rotation and magnetism, because in the limit where both of these phenomena are weak, rotation basically splits the multiplet evenly, so it shifts m equals 0 not at all. It shifts plus and minus 1 in opposite directions. But magnetism in general doesn't have to do this. The magnetism could be in general any sort of geometry, but even like a generic geometry is expected to be associated to some asymmetry. And so this, by the way, this paper is quite interesting. It was from last year. It's a Nature paper. It's basically one of the big claims in the paper is you can use this asymmetry to rule out certain magnetic field geometries in the interior of the star. But here's where I come in, right? So this is my talk. I get to talk about whatever I want. Let me just walk you through this logic, right? So I'm claiming that about 20% of red giants have suppressed gravity modes due to magnetism. And then I'm also claiming that now we can measure frequency shifts associated with fields which are not quite strong enough to cause suppression, right? But then it seems like reasonable to expect then that there should be there should be in this parameter space of red giants some stars which are not appropriately described by perturbation theory, because we know that there are stars that are suppressed at that, like above that magnetic field scale. So I'll just quickly describe how we actually handle this problem. It's a little bit, I'm not going to get into the weeds of it, But essentially, we can try and remember this assumption that I'm making, that the G modes are high radial order, which means that the radial wavelength is very small. So you just imagine like some wave, but that varies very quickly in radius and not as quickly in the horizontal angular directions. And it turns out what that allows you to do is it allows you to separate the radial and the horizontal equations. The radial equation is just sort of like a WKB propagation equation. But the horizontal equation looks like this. So don't worry about all the details, but I will say there's some parameter here which governs the effect of rotation non-perturbatively, and then there's some effect which governs the effect of magnetism also non-perturbatively. And the only thing that I really want you to take away from here at the moment is if I set both these parameters to 0, this is just a generalized Legendre equation. So it's solved by spherical harmonics. So the interpretation of all of this procedure is that we're basically translating the effect of rotation and magnetism together into this eigenvalue problem, which we can just sort of generically solve independent of a stellar profile for like generalized version of spherical harmonics. And if we understand those like numerically, we have those eigenvalues, then all we do is we go into whatever method that we like the most and we replace L times L plus 1, the standard thing which appears all over, in the spherical harmonics. We just replace it with lambda everywhere. Don't think about it. And so this procedure has been well known for just rotation in the past. It's called the traditional approximation of rotation, which I think is an awful name. And it's even more awful when you do it for magnetism, and then you've basically like sort of name a new approximation and then you call it the traditional approximation in your paper. But anyway, so this is like a generalized version of the traditional approximation, if that word means anything to you. And I'll just go over some brief results of what happens when you implement this, solve that equation and implement into these sort of pulsation solutions. Here's an example of, just another example of what this sort of period of shell diagram looks like. Again, this folded period of the modes as a function of mode frequency. And we just sort of make a synthetic version of this for some reasonable star on the lower red giant branch, just the MESA model. And we do it using our procedure, and we also do it for a perturbative expression. So by the way, I should say that for simplicity, we have restricted to the case where the magnetic field geometry is a dipole aligned with the rotation axis, although in general, it can be generalized if you would like. The point is that the solid dots here are the non-perturbative expectation versus the perturbative expectation prediction, which is the hollow points. And you see that in general, the frequency shifts are quite a bit stronger, especially towards the suppression scale. And what the way that you should think about this is that when you're close to the suppression scale and you're just using perturbation theory, you're likely to overestimate the field that you're measuring because you're going to think that the field that you need to make that frequency shift is larger, for example. So that's just one way in which perturbation theory might matter. Non-perturbative effects might matter, I should say. But you can also sort of play this game with things like G-mode pulsators. And so one family of G-mode pulsators, for example, is these 1.5 to 2-ish solar mass stars called Gamma Doradus stars. So I've just plotted here the Brunt profile for such a Gamma Doradus model for something which is very close to the ZAMs, and then something which is quite evolved in the main sequence, so close to the terminal age main sequence. And then I've plotted it, the mode calculations, basically the period spacing, but as a function of period, as I said, for just magnetism, just rotation, and then the combined effect of the two. And you see that they both qualitatively introduce some kind of trend. But that trend is quite different. First of all, there's a different dependence on the azimuthal order M. So for example, if you have a aligned dipole magnetic field, the M plus and minus 1 modes can't distinguish between the direction of the field, so they're actually degenerate still. Whereas rotation clearly breaks that degeneracy. But also at the suppression scale, so this critical frequency scale where you expect suppression, you basically have like a large amount of quote unquote curvature in this diagram, which is not really associated to rotation, which doesn't have this suppression phenomenon in the same way. And then of course you can play the game and you can add both of those effects as well. And then I won't spend so much time on this except to just sort of point out that a prediction of our theory is that the suppression scale is actually a function of these angular numbers L and M, which means that if you somehow can do mode ID and like identify that frequency for multiple branches of modes, especially those of different M, we speculate that you should be able to sort of triangulate back out the field, the rotation frequency and also the field. That's not been done before, but I think it seems to be a straightforward prediction. Okay, so that's all I have to say. Here's my conclusion slide. These are basically the frequencies. This is like the very like sort of first order picture I'd like you to have in your head. I'm working on some other stuff related to this problem as well. And also, if you think that there's any sort of collaboration that's possible, then please let me know. I'd be very happy to think about it with you. Thanks. Thank you very much.
In the beginning, you said that P mode separated equilibrium frequencies and G mode periods. What happens if they couple?
That's a very good question. So actually, I sort of skimmed over this. Like, I actually didn't really mention this at all. But in the case of red giants, they're always coupled, right? So you actually generically, so the first order, basically, if maybe I can go to the spectrum of the red giants again. So this x-axis is actually frequency. So these like groupings of modes are actually equally spaced in frequency. But what happens is if you have coupling to G modes, that just introduces like what's called a period spacing, which is like kind of like a splitting, where basically you have multiple modes, which are you can think of kind of as the same P mode coupling to the different G modes, and they'll have slightly different frequencies, which will turn out to be roughly equally spaced in period, kind of. And so when I show diagrams like this, which are also red giants, and I've very much skimmed over this, this is actually not like the actual mode period. This is what's called the stretched period, where people basically compensate for this P mode coupling. But that's, I think, quite detailed. Yeah, it's very important to understand that actually. Yeah.
Thanks, Nicolas. It was really nice talk. I wonder which kind of observational constraints will you have for the analysis you do? Because you show Kepler stars.
Yeah.
I wonder if, for example, test data works for you, or which kind of observations you will like to expect, for example, for Plato, in order to follow up a possible correlation with stars that we already have, for example, Zeeman Doppler imaging maps, and if there is any relation with what you find inside of the stars.
Yeah, that's a good question. So just to give some context for the Kepler stars, we basically have like on the order of a few thousand red giants where this period spacing measurement is possible. You can also do like much more basic things using asteroseismology, which don't require, that much work, and you can just do it in like, I think a night or two or something, which is you can just get the mass and radius very quickly using this technique. But if you want the period spacing, like it's already a few thousand stars and that number is going to go up by quite a bit. I'm not so sure about the exact numbers with TESS. It's not currently possible, I think, to get period spacings, or at least for that many stars, because you have to have a pretty long baseline because you have to resolve the period spacing. I'm not so sure about Plato's numbers actually, but there's actually a really nice proposal, or I think it was a white paper written by Dan Huber, which was saying basically, there's this very nice plot in it where there is going to be like a ton of new period spacing measurements that are possible with the Roman telescope actually. And so, of course, Plato is more tailored to this. So I just imagine that there's going to be a huge wealth of information coming up.
If you were to put this in, I don't know if it's in a stellar evolution perspective, but what is different? This 20% of red giants that have suppression, what is different about them compared to the remaining 80%?
Yeah, that's a good question. So I would say like the expectation, I think we just sort of chalk that up to like some kind of scatter in the magnetic field that you might have at the core of a star. And also this suppression scale, I mean, so if I go over here, this magnetic field, depends somewhat on the stellar parameters. And so in particular, N and rho do evolve to some extent over the red giant branch. So this quantity does change, but it's roughly usually of the order of like 10 to the 5 or 10 to the 6 gauss. So I imagine that some of it's to do with scatter, and then some of it is just that the stellar structures are different.
The big cluster somewhere in the HR diagram,
so
it'll be more spread,
yeah, that's a good question. So one of the, I guess, like if you're looking for some kind of physical clustering, so one of the arguments that's been used to explain why this is probably magnetism, is that these suppressed stars, there's a paper by Denestello, that they're like basically all above, I think something like 1.1 or 1.2 solar masses or so. And the idea is that this is also happens to be like roughly the threshold of when you have a convective core on the main sequence instead of a radiative core. The idea being that, okay, you have some kind of dynamo thing happening, and then it freezes out into the core of the red giant. But if you don't have that convective zone at the beginning, then somehow you don't get it. That's kind of the story that I'm familiar with. But yeah, that's one example.
So I think you mentioned it, but I didn't quite understand, why is the field specifically coming from the core and not in the radiative zone? I mean,
Yeah, that's a good question. So I mean, like, so for the red giants, right? This is different than the main sequence stars, but for the red giants, the surface of the star is like right here. This is a convective zone, so the brunt is 0, which means it doesn't contribute to that integral, basically. Let me just say it like that. And so this is the core. So this is like the outer part of the radiative zone, and then here is basically the edge of the helium core. Right. So you're sensitive to the magnetic field here.
because the core's radiative and the envelope's not.
Right, exactly.
Yeah.
I will say, like, and I glossed over this a little bit, but for massive main sequence pulsators that I've been talking about, you actually don't have to disentangle the P and G modes. They're just right on the surface. So you don't have to play this game. In that case, you're not sensitive to the core, you're sensitive to something like the integral of some function of the field over the radiative cavity, which is like now more like the outer layer, kind of.
If I could just ask another quick thing. So you were showing at some point the period and the kind of strength of the field. Are you not more likely then to detect strong fields? And if you look at the star for long enough, would you get 1 kilogauss lower than a kilogauss potentially fields? Is that possible?
Sorry, less than 1 kilogauss. I think that would probably be difficult, but I'm not an observer, so I don't know the numbers exactly. Yeah. I mean, of course, I think, just like until the suppression scale, of course, if you make the field stronger, then it's easier to detect the field. But then, of course, you have to play this game if you can't have suppression happen. We don't actually understand so much how that happens, but the point is, if the field is sufficiently strong, we think that this is no longer possible.
Could you go back when you mentioned some of the Gamma Doradus later, and I seem to look into 2 predictions for, you said that this is basically just based on magnetic field strength, right?
Right. Yeah.
But you also mentioned that it has to do something with the age. Did I understand that correctly?
Yeah. Okay. So yeah, that's a good point. So because this is a sort of G mode asteroseismology, is pretty sensitive to the shape of the brunt profile. And so the way that these sorts of stars of like these these intermediate mass main sequence stars evolve is that you sort of start off with like a kind of, for the Gamma Doradus, you have like sort of a more flat kind of brunt frequency profile. But then as the star evolves, the convective core actually shrinks. And so you leave behind a compositional gradient because you have a varying amount of helium abundance. And so you see there's like in the evolved star, there's like this bump in the stratification. And then the reason why I've evaluated this model at a lower field is because basically our criterion for when we think suppression happens is when any layer of the star is resonant with the alphane waves. And so, but then the criterion for what the frequency shift is actually some integral of some quantity like that. And so basically you're sort of limited by this peak, basically. This sort of dictates when the suppression happens, roughly. That's kind of our argument.
Do you know what happens to these fields as the star evolves?
That's a good question. I'm not sure we really know, but I would assume that they just stay there because the magnetic diffusivity is quite low. And so like, I just imagine that they stay there. But if anyone who knows more about, magnetic field evolution has a different opinion, please let me know. I assume that they just stay there.
That would be great to explain all the white dwarfs that are magnetic and I don't know why. So if they stay there and emerge late for some reason, our problem is solved.
Yeah.
Maybe with pulsating white dwarfs we could probe.
Right, exactly. So that's what I think, yeah, it's for people like you that I have included this thing, right? So, yeah.
Notes taken.
Yeah, can you go back to that one of the Gamma Dorado? So basically, you're saying that this happens with time, right? So, what is the time scale for, let's say, for this change? Like, this is a factor.
From here to here,
Yes.
this is basically the main sequence lifetime of a 1.5 solar mass star. So I guess it's like a year or something like that.
This is long time scale, let's say.
Yeah, you're not measuring this variability over time.
Okay.
This is the evolutionary time scale of this star.
Further questions, comments? If not, then let's thank Nicholas again.
Yeah, I think.
And you.
Oh, yeah.
Final